is Seungchan Kim, and today I'm going to give a talk titled Multi-Robot Multi-Room Exploration with Geometry Q Extraction and Circular Decomposition. The type of problem that I'm interested in is an aerial robot exploration in structured indoor environment that looks like this in this video. The most conventional approach is that you can use frontier-based exploration where the aerial robots or drones can choose the frontiers or the boundary between known and unknown space as the next waypoints. However, it may not be good for adding context or prioritizing specific targets during explorations. The focus of this talk is exploration prioritizing rooms in a building. As you can see in this video, I'd like to focus on visiting rooms in indoor buildings rather than just uniformly increasing the coverage or spending too much time in corridors or hallways. And you might ask why. In many scenarios in indoor exploration, focusing on rooms is quite important because meaningful target objects of interest are most likely to be placed in rooms. So it needs more focused attention. Rooms are also structural segmentation units that constitute the buildings. Furthermore, I'd like to propose the scenario in which we deploy multiple robots that explore the buildings composed of multiple rooms. So the problem is how can we coordinate the behaviors of multiple robots exploring a building composed of multiple rooms? The approaches that I said was that we focus on the lighter point processing approaches, and there's no need for offline data set or learning-based models. And we chose decentralized distributed planning for multi-robot systems. This pipeline is composed of three components: the geometry key extractions, circular decomposition, and multi-robot coordination, which respectively deal with address the door and room detection, within room observations, and task allocation and planning. As for the first part, the perception pipeline, in an indoor environment composed of multiple rooms, the aerial robots generate 3D occupancy voxel grid from 3D point clouds, and then it generates a 2D binary occupancy map, from which it converts that to 2D distance transform map. We use this 2D distance transform map to perform geometry analysis. The first question that we have to ask is how we can find the doors, how we can model the doors or narrow passageways, as you can see in this video. So in order to model doors using distance transform, we can think of this diagram from top-down view. And there's let's think of the distance to the closest occupied cells. And there's a point in the middle. Now let's think of this red axis where it's aligned with the walls. If you think of the distance to closest occupied cell, this point in the middle is the local maximum along this axis compared to other points on this red axis. However, at the same time, this point along this perpendicular axis, it's local minimum along the perpendicular axis. Therefore, we can model this point as a saddle point in the distance transform. We argue that the door detection by saddle points extraction is quite effective, as you can see in this diagram, and we also validate that average precision and recall of this detection method was quite high. We can set the saddle points as a waypoint targets rather than merely using frontier-based explorations. Next, we can also use the local maxima from the distance transform to represent the room free space, because we can get the local maxima and that distance to the closest cell. By setting the local maxima and the distance as a center and the radius of the circles, we can generate a set of circles. The rationale behind using circular decomposition is that we can command the robot to reach the center of the circle to observe sufficient information about the room. Also, in the case of larger rooms, there's a circle split mechanisms, and the circle sets are dynamically updated. Another rationale behind is that it is very easy and efficient to keep track of which circles have been reached by which robots. As for the multi-robot coordination part, or the target assignments part of the multiple robots, what matters is the information sharing scheme. For multi-robot coordination, information sharing is very important. And we, in this pipeline, we let the robots share or publish the list of doors that they have reached, a set of circles that it has reached, also subscribe to circles and doors that other robots have published. By doing so, during the target assignment scheme, the robots can choose the next targets based on the shared information of other doors and rooms. The key point is that the saddle points and the circles are very memory efficient and concise representation of doors and rooms. As for the experiments, we did simulation experiments in 8 different environments, and this includes challenging scenarios including objects in rooms and walls are not aligning with the global axis. For the baseline, we used sub-UAV code base that we published in RSS, and we tested with up to 3 aerial robots. And we measured the number of surface focuses in rooms observed by robots collectively. For the real robot experiments, we used custom-built autoloaders. This is a qualitative behavior comparison between two robots, qualitative behaviors of 2 robots and 3 robots in simulations. As you can see in this video, each robot goes to each room, finds doors, and go into the rooms, observe the rooms, and they also avoid redundant explorations. If you compare the qualitative behavior between baseline and our methods, our method is good at detecting doors and going into the rooms, while the baseline often goes straight and just uniformly increasing the coverage. In the case of baseline, it often skips some rooms or multiple robots going to the same rooms together, but while in the case of our methods, all rooms have been reached by each robot, and it also avoids redundant explorations. This is a quantitative result where we measure the number of surface voxels in the rooms compared by our method and baseline, where our method performs much better than the baseline. And this is the video for real robot experiments where the drone can detect the doors, go into the rooms, go to the center of the rooms, sometimes going backward through the doors, spend some time in the door, in the room, observe the room, and there's multiple robots performing this task simultaneously and sharing the information across the robots and sharing the list of doors and rooms or circles that were reached by each robot, and that is being included in the target assignment schemes. Conclusion, we proposed an autonomous exploration pipeline that coordinates the behaviors of multiple aerial robots in a building composed of multiple rooms. And we used the geometry analysis to extract saddle points and local maxima for door and room detections, and circular decomposition of space for room observation and information communications. And we validated our method in simulation